In general chemistry, we were able to make really good predictions about the outcome of reactions. We studied 3 reactions specifically: the redox, the acid-base, and precipitation. And we were able to make predictions about those by understanding their mechanism. A mechanism is a physical process through which an event occurs. In our context, it's basically, what is the physical thing happening on the molecular level? What's the actual process happening in order to make this reaction occur? So I get it. I get we're going from one substance to another, but how? How are these atoms switching places? In organic chemistry, mechanisms become very important because our reactions get more complicated. When we were working with something like a precipitation reaction, it's okay, we've got a bunch of ions in this solution. If 2 of them hit each other and stick together better than the water can pull them apart, they're going to make a solid. Done. That's our mechanism. It's gloriously uncomplex. However, substitution reactions, our first reaction type, are going to have some complex mechanisms. We're going to be looking at these things. They're going to have an intermediate molecule that gets made. We're going to have multiple steps that we have to go through. We're going to need to be able to model where our bonds are going to and coming from. We're going to be actually drawing arrows to model these things. We're going to be drawing diagrams. This is going to be a little more complex. So in order to understand this, let's put some things into context. I have a reaction set up here. It's already predicted. And we're going to use this to go over some little bits of context. The first thing that we need to notice is that this is happening in a solution of water. All of our organic reactions will occur in a solution. We won't always be using water as our solvent. Whenever you see an organic reaction set up, if you see some element, some compound floating above or below this arrow, what that means is that's the solvent that this is occurring in. And as we saw when we started looking at our flow chart, that solvent is going to be important. It's going to play a role in how this reaction occurs. If it's protic or aprotic, or sometimes that solvent will be one of the reactants itself. Often, if I want to make something like an alcohol, I can take another organic molecule and run a substitution reaction in water to create an alcohol, to get that OH group from the water. So we can have some different kind of solvent that we're interacting with. So that's going to be important to note. That's where that's going to be listed, okay? So the other thing to note is this is all going to be occurring based on a collision. Remember, all of our reactions occur over a period of time. Even if they look instantaneous, it's only occurring that quickly because our molecules are moving very fast. For context's sake, I looked this up. There's a lot of very fancy math you can do to figure this out, but for something like hydrogen gas, H2, sitting at 2 atmospheres of pressure at 24 degrees Celsius, how many collisions do you think are occurring in 1 second? Just throw a number out there. It's going to be 3.46 e to something, E10. This is more than a billion. More than a billion collisions every second. So if we think about this, if we have that many collisions occurring, something that's a 1 in a million chance in this, 1 in a million chance, well, 1 in a million is happening 1,000 times every second. So when we start to look at the mechanisms by which these are occurring, it's going to be very important that we remember that things that have a low probability are still going to happen. They're going to happen a lot in real time. So the 2 mechanisms that we can have are going to be the SN1 and the SN2. Creative names. The S in both of those stands for substitution. Good, straightforward, clear. The N in both of these stands for nucleophilic, as in these are going to occur with a nucleophile. So we can go, oh, this is a substitution reaction. What's substituting? A nucleophile, period. So it's going to be important that we can identify the relative strengths of those nucleophiles, which is another reason why we want to know what's our solvent, because that is going to be a factor. So the one difference here is this 2 versus this 1. What do those reference? Well, those are going to reference a rate law. If you think back to kinetics, which you should be, since I mentioned collisions, we have specific rate laws. So let's go R for our rate. The rate of this reaction will be some reaction constant, and it's going to be second order. It's going to be both the substrate and the nucleophile. So the reaction rate here is going to be affected by both the substrate and by the nucleophile. Let's just write NuC for nucleophile. In an SN1 reaction, this is going to be first order overall. It's only going to depend on the substrate. In fact, that's our first clue that we have a different mechanism happening here. How could one of these be second order, where just by increasing the concentration of one of both of my reactants, either one, will make this go faster, versus having a first order reaction rate where, like in this one, it doesn't matter how much sodium I have, it's not going to make the reaction faster. It's only going to be occurring based on the concentration of propanol. So that difference is very important. So these are the basics of a substitution reaction. We're going to be working with a nucleophile, and we're going to be kicking off some functional group. We're going to call this the leaving group, and we're going to make a new molecule. So what we need to do next is learn about these two different mechanisms and understand how they work so that we can use them.